Now what we have is a 30 kilogram object, because when the two objects collide they stick together. We have a 30 kilogram object now with a momentum of 284 kilogram meters per second at 174 degrees. What's the velocity of that object? Well, we find the velocity by dividing the momentum by the mass. Momentum is mass times velocity, so clearly velocity is momentum divided by mass. We're going to have 284 kilogram meters per second divided by 30 kilograms at 174 degrees. When we divide this, we get 9.46 repeating meters per second at 174 degrees. Now we also want to compare the kinetic energy before and after collision. The kinetic energy before collision was the 1/2 times 10 kilograms times 20 meters per second squared, because this is the mass and the velocity of the first object. And then we do the same thing with the mass and velocity of the second object, and we get 3,440 joules. The kinetic energy after the collision we calculate by the 30 kilograms and the 9.46 bar meters per second, and I think it's only around 1,350 joules. We didn't really confirm that calculation. I did it in my head, so confirm it for me. Square this, multiply by 30, take half, and see if you don't come out around 1,350 joules. Kinetic energy is not conserved. There's no reason that kinetic energy has to be conserved in a collision. There's every reason why momentum has to be conserved. Remember that momentum is conserved because when two objects collide, they exert equal and opposite forces on one another, so that they have equal and opposite changes in momentum when they fly apart. Another part of the problem said, well, if in the collision we observe that the second object has a velocity of 4 meters per second at 310 degrees, then what is the momentum of the first object, and what's its direction and its velocity? Well, this tells us, the information tells us that the momentum of the second object is going to be 40 kilogram meters per second at 310 degrees. A 4 meter per second velocity on a 10 kilogram object. We still are going to have a total momentum of 284 kilogram meters per second at 174, but now we're assuming that they don't stick together anymore, but the second object is going to have this momentum from the information we're given. And we have to figure out what the momentum of the first object is. Well, the situation is like this, and this is really a pretty horrible looking diagram. I'm sorry I didn't have time to redo it. The class had to suffer through it, so I guess anybody who's watching this gets to suffer through it. But I think you can see what's going on if you look closely. We have the total momentum here, and we have momentum P2 here. That's at about 310 degrees, and if this is 40 kilogram meters per second, maybe this is 284. Actually, this one should be somewhat shorter, because this is only about 1/7 of this, and this looks like it's more like a third or a fourth. So it's not really drawn to scale, but you can get the idea. Now the point is, here's our P2. We're going to want a momentum P1, which when added to P2 gives us our total. Well, that momentum, when we add the P2, I've drawn P2 again here in red, it's going to have to be added to something to end up here. Well, that means that the first momentum is going to have to be like this, so when we add P2, we end up with this total. We can find the x and y components of P2. We get an x component of 25 kilogram meters per second and a y component of about negative 27 kilogram meters per second. And I'm not real confident of those numbers either. Take your 40 kilogram meters per second at 310 degrees and make any correction you might feel like you need to my figures here. And we'll go on with this in a moment.